Hey, hey dear students, today I am going to discuss the topic demonstration of the Stewart platform, which is your hands-on experiment topic. As you know, the manipulators are widely used for several decades for automation applications in industries. They are used for various automation tasks in industries such as material handling, pick and placing of an object, spray painting, spot building, etc. As we know, there are two types of manipulators. The first category is the serial manipulator, and the second one is parallel manipulator. Serial manipulators are similar to human arm and has open constrained kinematics chain linkage, whereas parallel robots have various closed kinematic loop structure. For example, whenever you are riding a cycle by one hand, it resembles to serial manipulation and it is less stable to manipulate, as you can think. Whereas riding cycle with two hands resemble to parallel linkage with good stability and stiffness. Riding cycle by two hands forming closed loop. While writing by a pen, our fingers also forming a parallel linkage. A dog also forming parallel linkage with the ground by his legs during motions. In 1928, the development of parallel manipulators was started to overcome the drawbacks and limitations of the serial manipulator, such as less stability, less stiffness, lower payload capacity, lack of preciseness and positioning, and less accuracy, etc. From then onward, various researchers such as Pollard developed the first spray painting machine based on parallel mechanisms. Guff developed a new tire testing machine for aircraft using parallel manipulator, etc. Testing of an aircraft tire was quite challenging those days due to high impact landing. Creating such similar simulating environment was quite challenging that time. Afterward, in 1965, Stewart made a popular 6 degree of freedoms device using 6 prismatic actuators for the flight simulation application. This device is used for aircraft pilot training and became famous as the Stewart platform. The Stewart platform is also used in various applications other than flight simulation in recent periods. The Stewart platform is the most popular form of a manipulator of all the classes of parallel manipulators. Other manipulators are also popular, such as Delta robot. It is a widely used robot in various applications in last decades. The mechanism of the Stewart platform has a complex closed kinematic structure with 6 degrees of freedoms constrained motion and has the capability to achieve the mappings. The development of this Stewart mechanism requires motion and force analysis for proper controlling of the same. Moreover, just opposite of the serial manipulators, kinematics, the Stewart platform inverse kinematics is more straightforward than forward kinematics. The serial robots kinematics, inverse kinematics is quite difficult. The development of this Stewart mechanism requires motion and force analysis for the proper controlling of the same. In the present demonstration, I want to show you physics instrument based The 6-6 spherical prismatic spherical SPS type of the Stewart parallel manipulator configuration. Physique Instrument is a company at USA. The platform consists of 6 prismatic joints connected to 2 semi-regular hexagon plate-like structures. One end of all linear actuators is connected to the fixed lower semi-regular hexagon plates vertices, and other end of the links are connected with moving upper semi-regular hexagon plate vertices. All vertices of both the plates are connected, implying 3 degrees of freedom passive spherical joints. The 6 prismatic joints are considered as the input joint variables L1, L2, L3, L4, L5, L6 to the manipulator to move the upper platform to the desired location. These are joint variables. A fixed inertial reference frame XYZ, capital X, capital Y, capital Z is assigned at the center origin O of the lower plate, with Z-axis pointed towards perpendicular to the plate is considered as reference point. Whereas a moving reference frame small u, small v, small w is assigned at the centroid of the moving plate at origin P, whose w-axis always perpendicular to the moving platform. The line joining the origin O and P is represented by a position vector P is equals to Px, Py, Pz. Furthermore, the positions of the moving stage is designated by a rotation matrix and location vector P. It is to note that the rotation vector is demonstrated by rotation about fixed x-axis theta x, y-axis theta y, and z-axis theta z, also known as the roll, pitch, and yaw angles, respectively. A vector theta is equals to theta x, theta y, theta z is expressed as the orientation of the top platform concerning the base frame. Therefore, the location of the top platform concerning the fixed frame is the term of location, and alignment of the parameters are articulated as Px, Py, Pz, theta x, theta y, theta z. It is required to adjust all 6 linear joints of the Stewart platform by a unique length vector L' to orient the center of the upper plate towards a unique location. An inverse kinematic expression for obtaining a specific unique set of link lengths that represent a given location x, that is parameters Px, Py, Pz, theta x, theta y, theta z for the upper platform. Forward kinematic solution that has multiple numbers of solutions in reverse of that. In the Stewart platform, you can see the 6 linear actuators. Those are giving a motion to the platform. These 6 linear actuators are nothing but conversion of rotary motion to the linear motion by some mechanisms. Those mechanisms may use as lead screw, rack and pinion, slider crank mechanism, etc. In the video, you can see a simple kinematic simulation of the Stewart platform is represented, in which a simple line diagram of Stewart platform is shown. 6 prismatic limbs are connected with 2 plates, that is lower plate and upper plate. You can also see the motion performing in this simulation. Those motions performing as rotation about Z, motions in Z direction, rotation about X axis and Y axis, etc. Students, it is time to present the actual demonstration of Stewart platform. In our lab, physics instrument based Stewart platform is here. This platform is very precise and accurate. It has accuracy within micron level. Getting a high accuracy increase the cost of the platform. This accuracy sometimes require in very specific applications to achieve the particular task. This platform contains a setup that is hexapod and a dynamic motion controller. That controller can be connected with the computer itself, and also we can connect other auxiliary devices such as joystick, keyboard, mouse, monitor, etc. This controller is also connected with the device that is hexapod. This setup has own user interface. By using that, some simple motions can be performed. Instead of that, we can also program our codes to give desired motions by different APIs. We can code in Python, MATLAB, LabVIEW, C programming languages. Now I am going to show the actual motions by using its own user interface. I will set at first velocity 20 mm per second. That is the maximum limit of the velocity for this platform. Different specifications are given in the data set. I will give some instructions to move the platform, such as motion in X direction, motion in Y direction, Z direction, and rotation about X axis, Y axis and Z axis. You can see those motions in the video. If you want to give a particular trajectory, you need to write different codes in the programming language used in this setup. Apart from that, in this user interface, Some macros are also available. You can make your own macros in this user interface. Thank you very much. So students, this is a user interface of this hexapod parallel robot. This user interface belongs to PI, that is Physics Instrument based company. This is US based company, and now I am going to demonstrate the motions using this user interface for this hexapod robot. So first I will connect using the LAN cable. It may connect another ways. So this software assigned the IP address and given to this platform controller. Now I will connect. So now it is connected. Now we will reference all the axes of this robot. So now the platform is referencing. You may feel some shaking of the platform. Now all the axes has been referenced. Now we open this interface. So here at this point you will find the velocity. So from 2 mm per second to we can set it maximum 20 mm per second. Now after setting the velocity, we will set a particular position. Let us suppose a 10 mm in X direction. There are some limited motions are possible. Those are given in data sheet. So after entering the 10 mm, I will click to the move to the target. Now the platform you will able to see to move. Now again I will try to set the 10 mm. Now negative 10 mm in X direction. You may see the platform is moving. Now I will put extra 10 mm to the Y direction. Also I will put negative 10 mm to the Z direction for the demonstration. Also this interface has one simulating platform, hexapod platform. You may observe. So whenever you give the commands, along with the actual platform, it will also move. So let us suppose again I am giving the 0 position, so it will move its original position. You may see the simulating diagram. It is also like in moving conditions. So now I want to rotate, let us suppose 10 mm in X direction, along about X axis. So I put the 10 mm, and you may see the platform is moving 10 axis in the X direction, about X axis. Now again I am putting the 10 mm, minus 10 mm about the X axis. So it will again come to the 0, then again it will go to minus 10 axis. Now coming to 0 position again. So similar, I also can move it, we can move it in Y direction as well. Let us suppose I am giving 10 mm in the Y direction. So now it is moving in the Y direction. You may observe. Again I am giving minus 10 mm in the Y direction. It is moving in the Y direction. Now come to the 0 position. So now time to give some Z axis rotation. So let us suppose I am giving the 10 mm in the Z axis rotation. So platform is rotating Z axis. Again I am giving minus 10 mm to the Z axis, so that you can see the more movement. Yeah, it is rotating in the. So also we can set all these 6 parameter independently. Let us suppose 5 mm in X direction, 5 mm in Y direction, and minus 10 mm in Z direction, some